Good evening, everyone. I hope this finds you doing well. This is going to be our second podcast of Chapter 3, and we're going to start with the introduction to the modern concept of atomic structure. Now, we've talked about the atom and how incredibly small it is. We're going to talk about how put some more thought into that and how they can be different from each other. So we can take a look at our atom and we know that there is a nucleus in the center of the atom. And we also know that the nucleus is positively charged. Well, why is it positively charged? Well, we can take a look at the nucleus and break it down into two particles. We have protons, and we will abbreviate them P with a positive charge. And then we have a neutron that will describe that as N, and it doesn't have a charge. So the protons are positively charged, and they are equal to what's called 1 AMU. An AMU is an atomic mass unit. You may want to jot that down. So 1 AMU is an atomic mass unit. Well, what is that equal to? Well, here it's 1.67 times 10 to the negative 24th grams. Think about that for a second. We know a gram is about the size of a paper clip. Well, if we're talking about 1.67 times 10 to the minus 24th, you can see a proton is incredibly small. And so they have just labeled this as one atomic mass unit. It just simplifies this kind of number. Well, when you take a look at a proton, we also say a neutron is also made up in the nucleus, and a neutron is also equal to 1 AMU. Now, the mass here is slightly different, but when you round it, it's going to be the same. And so that is also equal to 1.67 times 10 to the negative 24th grams. Incredibly small. So it's just much easier to say that one proton equals one neutron, which is equal to 1 AMU. Now, here's another part that's going to boggle your mind, is if we start taking a look at an electron. It's hard enough to even begin to visualize how incredibly small a proton and a neutron is, but then we have these electrons that are flying around on the outside, and we are going to abbreviate that E with the negative because electrons are negative. Well, the mass of an electron is 1 over 1,840 AMUs. Wow, excuse me, this is crazy. Or it's equal to 2,000, we kind of round that up, about 2,000 electrons is equal to one proton, which is also equal to one neutron. So for all practical purposes, we pretty much say that electrons do not have any mass because it is so incredibly small. So now if we take back and look at this, you can see that our nucleus is positively charged because I have my protons that are positive, my neutrons that do not have a charge. But then when I take a look at my electrons that are negative, I have this positively charged center, I have this electron shell around the outside that is negative, so that makes the atom overall neutral is what you should be saying in your head. Okay, so as we move along, let's give this a little bit more substance about the size. We can say that volume occupied by negatively charged electrons is approximately 1 times 10 to the minus 10th meters, which is equal to an angstrom. Again, we have this nucleus, which is 10 to the negative 15th, and you can see the different parts that we just talked about. Protons are positive, neutrons do not have any charge. So on average, an average atom has a diameter of about 1 angstrom, incredibly small. And we've done a little bit of work on this in class also. So now we'll come back to this in just a second. We're going to start talking about isotopes. So if we take a look on the periodic chart, you can see that this is the most common form that you are going to find most of these elements in nature. But we do have some called isotopes. If you are writing with a pencil right now, that's one good isotope that we will talk about in just a second. So isotopes are atoms with the same number of protons, but different number of neutrons. So we've talked about in class, where do these numbers come from? The protons, remember, are the atomic numbers, and the neutrons, we're going to take this number rounded and subtract the 2. So we've done some work with this, in finding the number of protons, neutrons, and electrons. Now, another thing that we need to take a look at is isotopic notation. So this is a really good diagram here to show you that in our nucleus we have 11 protons and we have 12 neutrons for sodium. So let's take a look at where those numbers came from. So here's sodium. Let me grab a different color here. It's right here. So 11 protons should make sense to you because that's our atomic number. And we took 22.99 and rounded that to 23. So most periodic charts will have the atomic number on the top, the mass number on the bottom. Now if you look at the isotopic notation, just because we like to confuse you, you can see that they have flipped that. When you see isotopic notation, you'll always see the mass rounded on top with the atomic number on the bottom and a symbol as to what element it is. Now, if I look at the difference between these two diagrams, I can check off, I got the same number of protons. Well, that better be true because different elements can have different number of protons. So if I have sodium, it's always going to be 11 protons. But here you can see that I have 12 neutrons in this example and I have 13 neutrons in this. This is what an isotope is. Now because this is the one that's on the periodic chart, this is the most common form. But this does exist in very small amounts. So you can see again, I have the differences. It's a mass number on the top, and the atomic number always has to be the same if this is going to be sodium. So the atomic number is equal to the number of protons in the atom. Remember that protons are positive. All atoms of a given element have the same number of protons. So all carbon atoms have 6 protons. So how is it neutral? Hopefully you're thinking in your head, well, if it has 6 protons, in order for it to be equal, it better have 6 electrons. And indeed, that's what it has. All right, then we take a look at the mass number that we have also mentioned. It's the total number of protons and neutrons. From the periodic table, the mass number is equal to its atomic weight, which is rounded to the nearest whole number. This gives the average mass of a number. So maybe a favorite element of some of you is gold. So if I take a look at that, I wrote down gold 197. So I go back a couple of slides. Here is gold. And you can see that indeed it is 197.0. So I rounded it to 197 and its atomic number is 79. So that's where those numbers come for that isotopic notation. And again, you can see that the mass number is on top and the atomic number is on the bottom. So we are going to be applying this when we take a look at our isotopes. So if I take a look at hydrogen, now hydrogen exists on the periodic chart as 1, 1. So let's take a look at that one more time. Let me see if I can pull back that periodic chart. Here it is. So if I take a look at hydrogen, you can see that it has atomic number 1 and the mass number 1.008. That would round to 1. So that is the most common form of hydrogen as an isotope. Now if you look at this slide again, you can see that I have hydrogen 1, hydrogen 2, and hydrogen 3. Again, this is the one on the periodic chart, so that's the most common form. Make sure you're jotting that down. But I do have these other two that exist. So how are they different? You can see by my key, a proton is my blue sphere here, 1, 1, 1. That better not change because I have hydrogen. The atomic number cannot change. Number of electrons, 1, 1, 1. Here again, that can't change for this, otherwise it's not going to be neutral. Now here's my neutrons. You can see in the first part, the neutrons do not even exist. Here I have 1 and here I have 2. So how do I write this in isotopic notation? Mass number is 1 because by this number right here, hydrogen's atomic number is always going to be 1 due to 1 proton. Hydrogen 2. So I write down my symbol, I write down the mass number on top, and again I have 1 proton. That's what makes it hydrogen. Hydrogen 3, how do I write this? Hopefully you already have it written before I do. The mass number goes on top and the atomic number goes on the bottom. So this is showing you how the isotopic notation works. Okay, so we are going to talk about these three problems in class. So I am going to stop right now, and this will be the conclusion of our second podcast. Have a great night, and I look forward to seeing you in class. Stop.